How the pure substances change phase. There are many practical situations where two phases of a pure substance coexist in equilibrium. For example, water exists as a mixture of liquid and vapor in a kettle. Attention in this section is focused on the liquid and vapor phases and their mixture. The compressed liquid and saturated liquid phases. As a familiar substance, water is used to demonstrate the basic principles involved. Remember, however, that all pure substances exhibit the same general behavior. To establish these phases, let us consider a piston cylinder device containing liquid water at 20 degrees Celsius and 1 atm pressure. We denote it as state 1. Under these conditions, water exists in the liquid phase and it is called a compressed liquid, meaning that it is not about to vaporize. State 1 can be presented on a temperature volume diagram as shown. Heat is now transferred to the water until its temperature rises to 40 degrees Celsius. As the temperature rises, the liquid water expands slightly, and so its specific volume increases. To accommodate this expansion, the piston moves up slightly. The pressure in the cylinder remains constant at 1 atm during this process since it depends on the outside barometric pressure and the piston's weight, both of which are constant. Water is still a compressed liquid at this state since it has not started to vaporize. The new point of the substance temperature and cylinder volume on the temperature volume diagram can be depicted. As more heat is transferred, the temperature keeps rising until it reaches 100 degrees Celsius. At this point, water is still a liquid, but any heat addition will cause some of the liquid to vaporize. That is, a phase change process from liquid to vapor is about to take place. A liquid that is about to vaporize is called a saturated liquid. Therefore, state 2 is a saturated liquid state. State 2 is added in the previous temperature volume diagram. It can be visualized as shown. Once boiling starts, the temperature stops rising until the liquid is completely vaporized. The temperature will remain constant during the entire phase change process if the pressure is held constant. During a boiling process, the only change we will observe is a massive increase in the volume and a steady decline in the liquid level due to more liquid turning to vapor. Midway about the vaporization line, the cylinder contains equal amounts of liquid and vapor. We denote it as state 3. State 3 is added in the temperature volume diagram. As we continue transferring heat, the vaporization process continues until the last liquid drop is vaporized. We signify it as state 4. The entire cylinder is filled with vapor that is on the borderline of the liquid phase. Any heat lost from this vapor will cause some of the vapor to condense. A vapor that is about to condense is called a saturated vapor. Therefore, state 4 is a saturated vapor state. State 4 is illustrated in the given temperature volume diagram. A substance at states between 2 and 4 is referred to as a saturated liquid-vapor mixture, since the liquid and vapor phases coexist in equilibrium. Once the phase change process is completed, we return to a single phase region again, this time vapor. Further transfer of heat causes an increase in both the temperature and the specific volume. Let us say the vapor's temperature is 300 degrees Celsius and we denote it as state 5. If we transfer some heat from the vapor, the temperature may drop slightly, but no condensation will occur as long as the temperature remains above 100 degrees Celsius. A vapor that is not about to condense is called a superheated vapor. Therefore, water at state 5 is a superheated vapor. State 5 is shown in the temperature volume diagram. This constant pressure phase change process is illustrated in a temperature volume diagram, or usually we call it as TV diagram. Suppose the entire process described here is reversed by cooling the water while maintaining the pressure at the same value. In that case, the water will go back to state 1, retracing the same path, and in so doing, the amount of heat released will exactly match the amount of heat added during the heating process. Let us recall ourselves. This figure illustrates the constant pressure phase change process of a pure substance on a TV diagram. Each state has its own criteria regarding the phase type, temperature, volume, pressure, and other related properties. Based on the illustration, we can infer that a pure substance exists in different phases depending on its energy level. In the liquid phase, a substance that is not about to vaporize is called a compressed liquid. In the gas phase, a substance that is not about to condense is called a superheated vapor. The simplified version of the TV diagram for the heating process of water at constant pressure at 1 atm is presented here.